Willing from NC State. I'm your session chair for our divided session 1A. So this is the mobile security session. We're going to have 2 papers, and then our break, you come back and have the remaining 4 papers in the session. So to get us started is Emmanuel Staff, and he's going to be talking about new ways of using TrustZone to provide some capabilities for user space applications. Emmanuel?
Thanks for the introduction. So good day, everyone. So I would like to talk about a new security architecture which we propose and which we call Sanctuary. Now, the research problem we are actually dealing here with is the question of how we can construct an ecosystem of mutually distrusted enclaves on mobile devices. So now you may ask why this is actually something we want, mutually distrusted enclaves. And I will answer that question, but first I will give you some background on the topic. So now a sensitive app on a mobile device can be any app that protects any kind of sensitive data. So let's just think about the classical mobile payment app. An operating system is not providing enough protection for such a sensitive app. It only provides a software-based isolation. So this is indicated on the figure with the dotted lines. So if a malicious app is able to exploit a vulnerability in the commodity operating system, then the sensitive apps get compromised. Now, what industry provided already 15 years ago as a solution for that is ARM TrustZone. So what ARM TrustZone does is that it splits the system into 2 worlds, into the normal world and the secure world. And on the normal world, we will run the commodity operating system and all the non-sensitive apps. And on the secure world, we will run the trusted OS and the sensitive apps. So the sensitive apps and the trusted OS together are often also called the trusted execution environment. And the trusted OS here will be provided by the device vendor, and the sensitive apps will either be provided by the device vendor or by third parties that want to protect their code. So the big question now, what I forgot, there's also the trusted firmware running in the highest privilege level underneath, and the trusted firmware is here for performing the context switch between the 2 different worlds. Now, the big question is if TrustZone is really the solution we are looking for. Now, TrustZone is actually used quite regularly on modern mobile devices, and the trusted OS contains a lot of functionality today. So what we are actually getting here is we have the same problem on the secure world now that we already have on the normal world. So if a sensitive app is also able to compromise or to exploit a vulnerability in a trusted OS, then again all the sensitive apps will be compromised. Now this means that all the sensitive apps in the secure world need to be trusted. And establishing trust always comes at a cost. So deploying third-party apps in TrustZone is very costly. And on a lot of mobile devices, actually, it's not even possible. So the device vendor locks TrustZone completely. And that means that on today's mobile devices, a lot of sensitive apps that actually should be protected are not protected. Now, the problem of TrustZone that causes all of this is actually the TrustZone just provides one single TE, so one single security domain. And so to sum it up, TrustZone is not the solution we're looking for. So what we would actually want is an architecture that could provide us with multiple security domains, and this is what the Sanctuary can deliver. So what we want to do is we want to remove all the third-party code from the secure world and just keep the code from the vendor inside. And then we want to isolate the different sensitive apps in the normal world and run them as user space enclaves. And we want to get a strong hardware-enforced separation between the sensitive apps so that if, again, a sensitive app is malicious, it cannot access the commodity OS and also not the other sensitive apps. And if we can achieve that with our security architecture, then finally we don't have to trust the sensitive app anymore, and we can make the TrustZone protection available for all the third-party developers. So we know now where we are today with TrustZone and where we want to go, but on the way there are a list of challenges that we have to face. So actually the mobile market is dominated by ARM architectures. So for such an architecture, you do not want to design new hardware components that do not fit in the ARM ecosystem. Second challenge, we do not want to replace the existing code bases. So as I said, TrustZone is already quite frequently used, and the vendors already have their trusted OSs, and we do not want to replace them completely. And as a third challenge, we only want to have a minor impact on the commodity OS. So the adversary model that we usually assume for such a security architecture is one where the adversary can compromise all of the code in the normal world, so on all privilege levels, and it can even run a malicious sensitive app. But what the attacker cannot do is that it cannot compromise the trust zone, because this is the trust anchor here, and he will also not perform physical attacks. Now, before we go to Sanctuary, I want to talk about the existing research proposals. So we categorized these into 3 different groups, starting with the software approaches that utilize TrustZone. So what these approaches do is that they improve the isolation of the sensitive apps without any additional hardware features. Then next to that, we have the hypervisor-based isolation approaches that utilize TrustZone. So what they're doing is they use the virtualization. They use virtualization to protect the sensitive apps, and they use TrustZone as their trust anchor. And the third group are proposals that use architectural modifications. So here the authors try to overcome TrustZone's shortcomings with own hardware. Now, the problem is with all of these approaches that actually they do not tackle all of the challenges that we shown before. So for example, for the software-based approaches, what we have to do here is that we have to replace the existing code bases. And for the hypervisor-based solution, we have an influence on the commodity OS, and we also block the hypervisor for other use cases, which we might use the hypervisor for. And the last group, the architectural modifications, okay, that's pretty clear. We have to introduce a new hardware design, which you do not want. Now, besides of these problems, there are also other problems that you could categorize to the different groups. So now we will come to Sanctuary. So what we want to do with Sanctuary is that we want to tackle all of the mentioned challenges at once and provide a multi-domain isolation. So when we look at the figure on the left side, what we can see is how the initial setup for Sanctuary would look like. So let's assume we have a physical core A, and this core runs in the normal world, as usual, the non-sensitive apps. So we use the secure world as our trust anchor, but as said before, we want to remove all the third-party code from the secure world, and what we will keep in there is only the code from the device vendor. So here we will now call that security primitives. Now, since we are running on a mobile device, we can assume that we have multiple cores. And actually, each of these cores will be able to use the security primitives in the secure world. So they are not copied to each core, so of course, they are just mapped. So every core can access the same security primitives. And so now at one point in time, we might want to execute a sensitive app. So what Sanctuary is doing is that we are using TrustZone features to isolate one of the physical cores. And if we have done that, then we can run a sensitive app as a user space enclave in the normal world, but only on this core. Now, a sensitive app, again, can be any app that needs to protect data. So you could think of these classical use cases, again, like mobile payment. You could think about use cases that are somehow cool at the moment, so like cryptocurrency app, or also like machine learning algorithms. So these algorithms, it might be interesting to protect them because they might use some proprietary model which the vendor wants to protect. Or you could also think about future use cases, for example, like a digital key or a digital car key. Now, if we want to execute another sensitive app, we can either wait until the first sensitive app finished its execution, or if another core is available, we can use the feature to isolate another core and run another sensitive app on this core. So what Sanctuary gives us with this setup actually is that we can set up, like I said, an ecosystem of enclaves where we run the sensitive apps in user space. And we will isolate them strongly using hardware features. So if we are revisiting our challenges from the beginning, we can see that, first of all, we do not need a new hardware design because we just use features provided by TrustZone. The vendor can actually keep their code in the secure world and use it as the security primitives. And third, we do not heavily influence the commodity OS, since we are only isolating the core as long as the sensitive app is running, and after that the core is given back to the commodity operating system. So now about we will dig into some of the technical details of Sanctuary. So first we will look at how a TrustZone actually works. So when we now look at the lower part of the picture, we can see how it works in hardware. So for TrustZone, the memory is actually split into the two worlds. We have the normal world, we have the secure world. And the splitting is actually done by the memory controller. So what the memory controller will do is it will use something which is called the non-secure bit, which is part of the bus transactions that are actually sent by the cores when it tries to access some memory. So the value of this non-secure bit is set by the core, and it depends on in which mode he's running. So it could run in the normal mode or in the secure mode. And depending on the mode, the non-secure bit is set, and depending on the value of this bit, the memory controller will perform memory access control. So this is how TrustZone looks on the hardware side, and on the software side, this is actually nothing new. We already saw that before. So we have splitting in normal world, secure world, and the trusted firmware running underneath. So this, what you can see now, is just a standard setup how it looks like with TrustZone. So ARM actually provides a reference implementation for this memory controller here, and they call it a TrustZone address space controller. And in its newest version, this memory controller has a nice little feature which is called the identity-based filtering. So actually this feature was implemented to bring secure UI to TrustZone. But what we are doing is that we exploit this feature for something else, for Sanctuary. So what we are proposing is that you assign unique IDs to the cores. And what you can then do with it is we're using another part of the bus transactions sent by the cores, which are called the non-secure access ID bits. So when assigning unique IDs, though they will be sent as part of the bus transactions. And the memory controller can now use those bits to separate the normal world between the different cores. And what we can do with that is that we can build Sanctuary. So what we do is, I already mentioned that, we will remove all the third-party code from the secure world, and we will just keep the security primitives in there. And if we are now want to, again, execute a sensitive app, what we do is we will reconfigure the memory controller, and then we will split the normal world memory and will assign a part of it to our Sanctuary core. And in this core, we will then run our sensitive app as the user space enclave, and again having the security primitives in the secure world. And what you have not seen on the slide before is actually the Sanctuary library. So this is also provided by the vendor, and it provides some management functionalities. But what's important to mention is that it's not part of the system TCP because it's still running in the normal world. So we implemented a proof of concept on Sanctuary, and now I would like to talk a bit about the evaluation of it. So first, about which kind of security guarantees Sanctuary already can give us. Now, Sanctuary can protect the sensitive apps from a compromised OS, and it can protect the apps before they are running, while they are running, and also when they are finished with the execution. Sanctuary can also protect from a malicious sensitive app. So a sensitive app cannot access the operating system, the commodity operating system, and the commodity operating system cannot access the sensitive app. So we get a two-way isolation. And we can also protect from cache side channels, and we can do that by flushing the exclusive caches when switching to the Sanctuary, and also by excluding the sensitive app code and data from the shared caches. Now, when we are looking at the performance evaluation, so the Sanctuary lifecycle would look like this. Let's say we have a physical core, and it will execute at some point in time the OS. And then there is the execution of a sensitive app triggered. So what the core will do, it will actually set up Sanctuary, then it will execute the sensitive app. So keep in mind here that the execution of the sensitive app is only done on this one core. So all the other cores can still execute a normal commodity operating system. So it is not suspended. When the execution is finished, the sanctuary will be teared down and the core will be given back to the operating system. So actually the most interesting part here to measure is actually what kind of overhead sanctuary produces. And what we measured is how long the sanctuary setup and tear down for our proof of concept took. As mentioned before, we want to protect from cache side channels. So this is why we will exclude the sensitive data from the shared caches. And for the measurements here, we also did that. And we measured that over 100 consecutive runs. So for the sanctuary setup, we ended up with something like 440 milliseconds, and for the sanctuary teardown with 110 milliseconds. Now, but what we also wanted to do is measure how like an end-to-end use case for the user would look like. And this is why we actually implemented a one-time password generator, which a user would use in a normal two-factor authentication scheme. So what the user would do is when he is installing such an app, that one time he has to provision an OTP key, so one-time password key to the device. And this would take him around 1.2 seconds. And displaying the OTP would take him around 600 milliseconds. So the last part I would talk about are the code modifications. So because, as I said, we want to reuse existing code and not replace it. Now, as the security primitives, we actually reused OPTE, which is an open source TE. And we modified around 530 lines of code. For the ARM trusted firmware, we actually reused the ARM trusted firmware provided by ARM, the reference implementation, where we had to change 92 lines of code. And for the sanctuary library, we used the Circon model kernel, which gives us a fully fledged user space, and we modified 211 lines of code. So as a conclusion, Sanctuary provides an ecosystem of mutually distrusted enclaves on ARM devices. Sanctuary does not introduce new hardware features. Sanctuary does not replace existing code bases, and we also have not a heavily impact on the commodity OS. So currently, what we are focusing on is implementing further use cases like IP protection of machine learning algorithms that I mentioned, or also the digital car key. And we also want to bring some of the features of Sanctuary to the RISC-V platform. Okay, I'm not sure if we have time for questions, but you can also write me an email.
Chris Fletcher from Illinois, very nice work. Can you comment a bit on the key hardware primitive that any type of platform would need in order to support Sanctuary?
What type of platform? Yeah, so as you see, this is all targeted to ARM devices. And what you would have as a hardware requirement is actually that you are using a memory controller that has this identity-based filtering feature. So speaking of ARM, if you want to know the name, is the TSET C400. So this is the newest implementation of this TrustZone address-based controller. And a part of that, the only thing that you need is that you assign unique master IDs to all of the cores. So actually all the devices already assign master IDs to the cores, but now they just assign the same ID. So every core will just have the ID 0, but we need unique IDs.
Great, thank you.
Thanks.
Trent Jaeger, Penn State, thanks for the talk. Can you compare this to the Trust Shadow system from Mobisus 2017?
To which, sorry?
It's called Trust Shadow from Mobisus 2 years ago. We could take it offline, I guess.
Yeah,
I'm
sure.
wondering, so if you have a sensitive app and it's going to make a system call, do you decide, do you handle some of them in the local library and forward some of them to the untrusted OS, or how do you handle?
Yeah, actually the system calls are handled by the Sanctuary library. Okay. But the sensitive app in Sanctuary can still communicate with the security primitives in the secure world and also with the normal world apps, so over shared memory. But the normal system calls, let's say, for example, if you want to do some exception handling or whatever, this is done by the Sanctuary library. So you do not have to get out of Sanctuary for that.
Okay, thanks.
Thanks.
Hi, Gülis Tunjai from University of Illinois. I think you might have just answered my question, but I was wondering how IPC is affected by Sanctuary and by basically...
Sorry, how what is affected?
IPC, inter-process communication. If an app in a normal world wanted to communicate with
Yeah,
another app
do you want to, you mean when you want to communicate with the normal world?
Yeah, can
Yeah.
they still do that?
Yeah, actually this is kind of like the communication, how it works now with the normal world and the secure world. So you would just use a shared memory, and then the driver in the device driver in the commodity operating system and also the sanctuary library will manage this communication. So if you want to communicate with the normal world and send some non-sensitive data.
Okay,
Yeah.
awesome, thank you.
Can you expand a bit on the virtualization? So especially when you say that if you just spawn up multiple VMs for this, you cannot use virtualization for anything else? This is in the paper.
Your question was on virtualization, but I didn't get
So
the second part.
one of your claims is that you cannot just spawn up a VM for each of these things, right? You cannot just use ARM virtualization for this. And one of the things that your paper says is that, well, if you used it for this, you just can't spawn VMs for anything else. I just wondered if you could expand on this.
Yeah, so the problems I see with the virtualization is that you actually influence quite heavily what you can do in the normal world. So you might want to use, so there are these hypervisor-based solutions, but when you're blocking the hypervisor for protecting your sensitive apps, then you cannot use them anymore to do what you would actually want to do in the normal world.
But why? I mean, why can't you just have multiple VMs, one for the normal world or multiple ones for normal world?
Yeah, because let's say you want to use a hypervisor to do what the hypervisor is usually doing, so you want to use it in some cloud environment. So this means that the hypervisor is actually getting really big, and you have to add this component to the TCP of the system, and it gets really big then. And this is what you actually do not want to do. So you could think about a very, very thin and small, tiny hypervisor that you could use, but then you will not get all the functionalities that you would need or want to have in a cloud-based environment. So you have a problem there.
It's a very quick one. All right. So you briefly mentioned it during your talk and also in your answer. You said that you need those unique IDs assigned to the cores. How are those assigned, and how do you make sure that they cannot get spoofed?
So the cores actually, all of these core, like I mentioned before in question before, already has a unique ID assigned. They are assigned in hardware. So actually, the only thing we are demanding is that we assign really unique IDs for the cores. Yeah. Yeah, thanks.